Hello meteorologists, and welcome back to Skybound on the Ground with Michael Lombard. We are on to part 2 of weather theory today, chapter 11 of the Pilot's Handbook of Aeronautical Knowledge. And since it's not actually raining, I'm going to lose this raincoat here. We are talking about, well, I promised you that we would figure out how clouds develop. Where do clouds come from? And to understand that, first let us take a look at the stability of air. Stability versus instability. Now, stable air is air that resists vertical motion. If you have some sort of a way that you try to get that air to start moving upwards, what it will do is it will dampen out that upward motion, and it will basically want to stop of its own accord. It doesn't want to keep on going. Now, if you have unstable air and you start getting it going upwards, it will actually continue going upwards and increase the rate at which it ascends. And unstable air is really where you get most of your weather coming from. Now, instability of an air parcel, it really depends. Stability versus instability really depends on the temperature and the moisture content. And those two things actually also have to do with clouds and whether we get clouds forming or not. Now, remember that air can hold a certain amount of water vapor in it. And you don't see that, but you can feel that sometimes if you have high humidity. Now, the example that the book gives us is pretty interesting. Say you have a cubic foot of air, and that cubic foot of air at 10 degrees Celsius will be able to hold about 9 grams of water vapor. 9 grams of water vapor at 10 degrees Celsius. What happens when you heat up that cubic foot of air to 20 degrees Celsius? You can actually hold more water vapor inside that amount of air when it's hotter. And so you will be able to hold up to 17 grams of H2O, of water vapor in there, and heat it up even more to 30 degrees Celsius, and you're actually going to be able to hold 30 grams of water vapor in there. And this is how we can actually measure humidity. We actually call it relative humidity because at each temperature there is a maximum amount of water that the air is able to hold. At 10 degrees it's 9 grams. 30 degrees is 30 grams. If you have that amount of water vapor in the air at that temperature, you're going to have 100% relative humidity. But say you only have 15 grams of water vapor at 30 degrees Celsius, that means you're going to have 50% humidity. So that's how you measure the relative humidity. And the reason it's relative is because, while the air at different temperatures can hold different amounts of moisture. Now, if you flip things around and you cool air that has a certain amount of moisture in it to a certain point where that moisture, where it becomes 100% humidity, the point at which it gets to 100% humidity is called its dew point. And if you cool the air further, if you cool it beyond that point, the air is not going to be able to hold the extra moisture anymore because it can't hold that much. And so that extra moisture is actually going to condense as liquid water, whether it's in moist little droplet format and it is clouds, or maybe it will even turn to clouds and then rain. So that is how you get clouds forming. And just to illustrate that, say we have air that is at 20 degrees Celsius, and it has 17 grams of water vapor in it, and we're going to cool that air down to 10 degrees Celsius, and so now it can only hold 9 grams of water vapor in it. The rest of that, those 8 grams, are going to condense into liquid water, and so you might get a little cloud forming in there, steam or something, or it might just all run down the side of the box. This is our imaginary box there. So that is how clouds are formed. And dew point is the point at which, when you cool the air becomes saturated, and if you cool it beyond the dew point, that is when you're going to get moisture condensing out of the air. You can actually, even by knowing the temperature and the dew point, you can actually even predict at what elevation you're going to have clouds forming. And this goes to the principle of how temperature cools as you go up higher in altitude. Dew point also changes as well, and so if you figure out the rate at which the temperature and the dew point converge, and you find out where those two converge, then you will know where the clouds are going to start forming. Well, it just so happens that they give us this number in Fahrenheit, probably because the Fahrenheit number works a little bit better than the equivalent Celsius number, but the convergence rate between how fast the temperature cools and how fast the dew point cools as you go higher is 4.4 degrees Fahrenheit. Okay, so what does that mean then? Let's say that we have air that is at, let's say 55 degrees Fahrenheit down here on the surface, and if the dew point is said to be 68 degrees Fahrenheit, and the temperature is 55 degrees Celsius, so that's the dew point, we can actually figure out at what elevation the temperature will have cooled to the point where the dew point is. And then that is going to be the elevation at which the base of the clouds form. So if we do our little math here, this is actually a difference of 13 degrees, and divide that by 4.4, and you actually get an altitude of just under 3,000 feet. It's actually 2,950 feet. And this is where the dew point, where the temperature will be the same as the dew point, and you will probably have clouds forming above that altitude. So that's pretty cool, and that is how you can use the rate of convergence between temperature and dew point to figure out the height of the clouds. So now that we know how clouds form, we need to figure out, there's actually several ways at which you can cool the air in order to get it saturated, because that's how you have to have, that's what you have to have in order for a cloud to form, is for air to become saturated with water, and it can't hold any extra water, and whatever extra water there is condenses. So there's several different ways that you can saturate the air in order for this to happen, and the first one is just say you have a relatively calm night, and you have air that is starting to cool close by the surface. So it's calm at night. There's no wind that's moving air and mixing it up. So what happens is the ground cools off, and it radiates all its heat off into outer space, and so the ground gets cold, and in turn it cools down the air that's right next to it. And so what you can end up getting is a little bit of a temperature inversion, where it's cool down here compared to the air that's relatively, we'll just say, put a W for warm, relatively warmer up there. And so it's this temperature inversion. Anyway, so the air that was down close to the surface cools down, and it will go down below its dew point. And this is actually how you get dew forming at night, because the air that's right next to the ground gets cooled off, and it just deposits the extra moisture on top of the grass and stuff. If it's cold enough, you'll get frost instead. And if this is a large scale enough, then you can also get fog, which is basically just a low cloud. So that is one way that you can get clouds forming. And when you have fog that is formed by this radiation cooling at night, we call this radiation fog. And this will be right close to the surface. Remember, fog is just a low cloud. It's within 50 feet of the surface. And radiation fog, it has its name because of the heat that's radiated off at night when it's a calm night, and nothing to do with atomic bombs or anything like that. So that's radiation fog. And so, yeah, when you cool air, that's when you're going to get moisture condensing out. So that's one way that we can get it saturated. Another way is somewhat similar, and this is by coastal regions. So what you can have happen is you have to have some sort of a breeze blowing, and where you have this warmer, moist air coming in from the ocean, and it comes in over cooler land. And as it cools down, then you get clouds forming. And if you have the clouds that form right at the low end, which that would be fog, we call this advection fog. And this is really dependent on wind blowing this moist, warmer air over a cooler landmass, and you'll get this in coastal areas, especially during the winter time. You can also get it during the summertime at night. You wake up in the morning and you have all this fog there because of the warmer air that moved in over the night and turned into fog. So this is called advection fog, and it can actually last for several days, and it's dependent on the wind moving that air in. So if you get up to like 15 knots of wind, that will really set the conditions right for this to form. If you have stronger winds than that, then they'll tend to dissipate stuff. But whereas with the radiation fog, when the day gets hot, the temperature burns off that fog. With this stuff, this can stay around for several days. So that's advection fog for you. And you can get the fog, or you can get the low clouds. So that's another way to cool air to its saturation point. And let's take a look at another situation. If you lift air, that's one way to cool it, because when you take the pressure off a package of air, it cools, and this is called adiabatic cooling. If you squish air together, it gets hot, and that's actually how a diesel engine is able to operate, because you compress the air, it gets really hot. All you have to do is add that fuel with a low flash point, and boom, you have your combustion going on. So when you squish air together, it gets hot. When you release pressure, if you lift it, it will get cooler. And if you have sufficient moisture in there, as it cools, that moisture condenses. So this will actually happen with if you have an unstable air and you start lifting that, and then you have these cumulus clouds start forming, and that air keeps on rising and rising, and as the moisture condenses, it gives off a little bit of heat, so that expands the air, which sends it up again because it gets lighter, and so you can get these towering cumulus clouds forming. That's how you get the thunderstorm developing. So that will be from lifting your air. And then you can also have something where you have perhaps a wind that is blowing air uphill. And when you have the wind blowing air uphill, it will, if it's stable air, it's going to try to resist that. And what will happen is you get this fog developing. And this is called upslope fog. So you can have upslope fog as a result of a breeze that is blowing the air, trying to blow this air uphill, and that once again is dependent on the wind flowing, and because it goes higher in altitude, it cools down, and that's how the moisture forms. Now here is a cool thing that we're going to learn about. We're going to learn a humongous word for a cloud type that's really fun to impress your friends with, and that is a special type of cloud that forms over mountain ranges when you get air that's flowing over it. So it's kind of similar to the upslope concept. You get this air that flows over it, and it forms this wave, and it's like a standing wave. Now the moisture that is in the air condenses as it gets to the top over here, and you see these lens-shaped clouds form. And we call these alto cumulus standing lenticular clouds, or just ACSL for short. And that's a nice bit. If you say that to your friends, their eyes will bulge. And it's actually really simple, because it's just putting a bunch of little cloud terms together. It's alto because that talks about the height at which it is happening. Cumulus, you've heard of cumulus clouds. Standing because it's in a standing wave, and lenticular because it's lens-shaped. So alto, cumulus, standing lenticular clouds. This signifies strong winds over a mountain range, and the reason why they form there is because this wave that's going over there, the moisture condenses at the top, and then as the air goes back downhill again, it warms up, and that moisture disappears. So it's actually a lot of moving air over there. The cloud itself just stays stationary, and that's why it's a standing lenticular cloud. So don't go flying in the mountains when you see these, because you're going to have a lot of turbulence that is resulting because of the high winds. So you can lift air in order to cool it to its dew point and get clouds forming. You can cool it by having it over a cooler surface, and that will do it. And then you can also, related to cooling it, is something called steam fog, and this will happen in the coldest times of winter time when you have a body of water again, and you move air, cold air, over this relatively warmer body of water, and the air starts taking on moisture from the water, and then it starts forming this steam-like clouds, and I guess it's said to look kind of like smoke as well. And so this will produce like low-level turbulence and icing and stuff, so don't fly in that because you don't want to get ice on your airplane. Alright, so that is how we can get, those are the different ways by cooling air just over the surface, by the colder land surface that the warmer moist air is over, by lifting air. You can also get it just by mixing warm air with cold air. So if you mix air together, then warm moisture air with cold air, that will cool it down, and you'll get clouds condensing and forming like that. Okay, so now let's talk about cloud classification. Let's start learning about some cloud terms here. And it's actually pretty simple how they break down clouds. It's just into four main categories, and it's all based on their height. So the first category is, drum roll here, low clouds. Oh, what do you know? It wasn't that hard. These go up to about 6,500 feet. The next category is middle clouds. Alright. And that goes up to about 20,000 feet. And then the last category is high clouds. Wow, so it's really not that complicated, is it? And then, sorry, that was the third category. We have four categories, and the last category is kind of all by itself, and that is clouds with extensive vertical development. So let's see if I can write that all out here. Extensive, and I'll just abbreviate it, vertical development. And those turn into thunderstorms. Okay, so here are our, let's take a look at these clouds. What you have in the low area is these, you'll often have like stratus and cumulus clouds forming in here, or some combination of both, where you have like strato-cumulus clouds, which is kind of like a mixture of stratus and cumulus. Stratus, just think like stratified, like a layer. It's a layer-like cloud. Cumulus is those puffy clouds that look like cotton balls. Now, here's another term that you'll learn, and that is nimbo. If you have some type of nimbo word inside a cloud name like nimbostratus or cumulonimbus, that just means rain. So if you have a nimbostratus cloud, that is a rain cloud, and rain stratus cloud. So it's pretty simple stuff. So that's the low clouds. Really the primary hazard of having low clouds is that they get in the way of where you're trying to go. And because when you become a private pilot, you are not certified to fly in the clouds, you have to make sure you can fly by the visual flight rules. And so this is going to present a threat to VFR flying. You got to make sure that you can see where you're going, and that you're not going to inadvertently end up in the clouds, because that always produces some type of an accident, or almost always. And you don't want to have that happening to you. It's always illegal. Okay, so those are the low clouds. If you go up higher and you get to the middle clouds, then you have some more hazards that that show up. And so when you see descriptions of middle clouds, you will have say this is a stratus type cloud. Middle clouds actually have the prefix alto to them. So alto stratus clouds or alto cumulus clouds. And alto actually means high, so just think higher than the low clouds. So alto cumulus. And you're going to get lots of moisture in these clouds, liquid water, and ice. You can get ice in the clouds because you're higher up and it's colder there. Turbulence and ice, those are going to be the two main hazards that you're going to encounter up there. And then when you get up to the high clouds, now you have these things that look like horsetails or just those high wispy clouds, and those are cirrus clouds. And cirrus clouds really have no icing threat and not really any turbulence threat either. They are actually composed of little tiny ice crystals, but because it's so cold up there, they're already frozen. They're not going to freeze onto your airframe surface. So those are the different cloud types, and now let's talk about clouds with extensive vertical development. This is the type of stuff you really want to avoid because they produce thunderstorms. So, extensive vertical development, that's just basically what happened when we talked about the unstable atmosphere. You get these updrafts, you start lifting air, and it keeps on wanting to go up. And as it goes up, it cools, moisture condenses, and as the moisture condenses, it gives off a bit more heat, and that will, in turn, provide more power for the air to continue moving upwards. And so you get these clouds that just tower up, and we call these towering cumulus clouds. They start off as those friendly little puffy cumulus clouds, and then they turn into a towering cumulus cloud. And these things can go up super high. They can go up to 50, 60,000 feet, and by that time it's going to be a full-on thunderstorm. And when it becomes a thunderstorm, we call that a cumulonimbus cloud. And you will have rain falling out of that cloud, of course, because nimbus means rain. So it's a cumulus cloud that has rain coming out of it. Now, I'm just describing the, let's just look at the life cycle of the thunderstorm. We kind of looked at part of it already. You have the cumulus stage where it's forming, where it's characterized by continuous updrafts, and so that is forming the thunderstorm. And then you have, so let me just write that down. And then you have the mature stage. And this is when the thunderstorm is completely developed. You might see this anvil shape at the top. And this is where you have all sorts of action going on. Updrafts, downdrafts, precipitation, lightning, hail, icing, extreme turbulence, all sorts of stuff going on. Maybe even tornadoes. Woo la la, we don't want to have that. Don't want to fly into that. So this is the mature stage. And this is characterized by updrafts and downdrafts that are going on inside the storm. And then finally, when the storm runs out of energy, it starts collapsing on itself, and it is characterized by mainly by just downdrafts as this storm starts collapsing. So, thunderstorms are probably one of the most hazardous hazards of aviation, and that's why pilots are told to stay away from them. When you have a severe thunderstorm, let me just draw that again. When you have a thunderstorm that has been categorized or classified as severe, you can have hail that is actually thrown out of the thunderstorm into clear air for miles away from it. And so you can also have extensive wind shear that is going on in the clear air around it. And so that's why they tell pilots that they should circumnavigate these thunderstorms by at least 20 nautical miles when you have some type of severe thunderstorm. Maybe it's been classified as severe, or you're looking on some sort of a weather radar display and it's showing up with intense returns on that display. So you got to make sure that you keep away from these things. If you flew through one, you can't fly over them because you have no way of getting that high in your Cessna 172. So you can't fly over them, and if you fly through them, you have the risk of your airplane being taken apart by the extreme turbulence that you're going to encounter there, or you might have the airplane just coated in ice because you're going to encounter those super cooled droplets in there, or you might just get pummeled with hail, and that will structurally damage your airplane. So there's also tons of water in there. Airplanes can get drowned almost when you encounter that much water. So thunderstorms are really bad things that you want to avoid, and I encourage you to avoid them because you will be a lot happier. Now, in the event that you do encounter a thunderstorm and you had accidentally found yourself, flying in the clouds maybe or something, and you got into an embedded thunderstorm, really the main thing is not to pull your airplane apart in the air, and that is you have to slow the airplane down to below maneuvering speed and then just attempt to remain in a level attitude without worrying about what your altitude is doing, because it's going to be going up and down like crazy with those up drafts and down drafts. So the main thing is just to keep your airplane upright, accept those variations in altitude and airspeed, and just keep that airplane flying in somewhat level attitude, and then hope you can get out of it. Okay, so now that I've scared you enough about thunderstorms, we have a little bit more to cover about air masses and fronts, but we are going to extend this to one more session, so we're going to do that in the next session. Join me next time for our last part on aviation weather theory on Skybound on the Ground.